The goal of this talk is to give an idea of the process of writing Rust abstractions for C code. What goes into that? And I'm going to use Configfs as an example. And so this is these slides are I just want to show off because they're actually it's in the shell. The presentation is in the shell. Huh? I don't know about you, but when I have to do slides, I always procrastinate a lot, get all kinds of stuff fixed and done. And then I found this tool that makes slides in the shell, and of course it's written in Rust, so called present term. You should go check it out. Now you can judge if it's good or bad. The shell, I think this shell is Kitty. It's not written in Rust, but there are shells written in Rust. You can go. I use a new shell myself as a daily driver. It's in Rust. So to do this, we're going to talk about Configfs and what it is. We're going to look at the C APIs and then how we turn them into something you can consume from a Rust driver. So what is Configfs? It's a pseudo file system. It allows you to control kernel objects from user space by creating directories, removing them, and writing to files. So when you create an object when you create a directory in this pseudo file system, you create a kernel object, and the properties of this or the attributes of this object will be exposed as files, and you can read and write these to configure your driver or interact with the kernel in some way. It's similar to sysfs, but it's the lifetime is sort of inverted. So user space controls when the objects are created and when they die. So in sysfs, you can sort of look into the objects in the kernel that is sort of managed by the kernel and get some feedback or interact with them. But in Configfs, if you create an object and then you try to unload your driver, you get the object will take a ref count on your driver and it can't go away. So user space decides when to destroy these objects. Oh, and also I have tons of slides. We don't have to go through all of them. I'm probably not going to be able to do that. So if you have any questions or something you want to discuss, just let me know and we can have a discussion. It's absolutely not important that we get all the way. So the data structures, the structure we have in Configfs on in the C code is we have a subsystem. So if you want to have if you want to use Configfs in your driver, you'll have instantiate the subsystem that you register. Then you have groups and you have items and you have attributes. Items are what appear as directories and attributes are what appear as files. The attributes that you have in a directory are determined by the item type. So multiple items can share the item type by pointing to it. Yes, so yeah, and a subsystem is a group. A group is an item by composition. So a subsystem includes a group, and a group includes an item struct. And yeah, that's it. Groups can have child groups. Items cannot have children. I don't know why it is that way. There's probably a good reason. It's just the way it is. I looked at it and I was like, we should collapse these into one because I think it does make sense. But
it's a little bit like directories and files. A directory is a file.
Yeah, but like a group is a group doesn't. So groups and the way I see it, groups and items could be the same thing. But I think maybe there is some legacy that I don't know about. Yeah, exactly. That's the point. Okay, so subsystem looks like this. You have the group, as I said, and you have a mutex to protect access to the structure. And you register your subsystem with the register, and you unregister it when you're tearing down your driver with the unregister. Pretty straightforward. Then you have your group, which has the item, which is what will appear as a directory. And then you have a list of children, which are also items. So groups can have children. And you have a backlink up to your subsystems. And you have your item, which is what it will appear as a directory. It has a name. I think so. You can, if it fits in here, you put it in here. Otherwise, you allocate, and you'll have a pointer here to the name. You have a ref count. You have a place to hook it into the list of the parent, and you have both a pointer to the parent group and the parent item, and the kernel, the code has this comment. Apparently, it makes some things nicer when you have both links. But I think one should be enough.
Is the emoticon part of the comment?
What?
Is the emoticon part of the comment?
No, that's me. That's me. For drama. Right? Yeah. So that's the way it is. Okay, so you have the items. The items have an item type, and that has two vtables for operations on the item, operations on the group, and then it has a list of the attributes, which are the files that will appear in your directory. And this one is the attribute list is a null-terminated array of pointers, so where the last entry is just a null pointer, and that's difficult in Rust. We can't have that, so we're going to look into how to deal with that. So the vtables we have. You have a make group and drop item in the group operations. Make group is, the kernel will call that in response to mkdir, make directory. It will call you make group, and you're supposed to return, I believe, you return a group pointer. So you allocate that and return it, and that gets inserted into the hierarchy as a directory. Drop item is called when you remove a directory, but before the directory inode and all the stuff is deallocated. And then the item operations, which again I think like they could be merged, but they have, so I cut out some here that are not important for this talk. Release, which is when the kref on the item goes to 0, this is used as the destructor. So now you can clean up and free your memory. And that is it. No, we have the attribute, which it's a file, right? So it has a name, it has an owner and a mode, which will be like read, write, execute for user group other. It has function pointers for what happens when the kernel should show this, like so read, and to store for write. So the kernel will call these when you read and write for these. There's some limitations on how you can read and write. I believe you have to write at most a page, and it has to be like in one chunk, which I think that makes sense, since it's just configuration data you're storing. It's not large amounts of data. And with that, you can now go and write a driver and have its configuration appear in Configfs. So you embed this struct Configfs subsystem in your driver. You define the item type for how your top-level directory should look. And you define this, for this item type, you define this null-terminated array of pointers to attributes. And then you register your subsystem, and it will show up in wherever you mount Configfs. Usually it's sys kernel config, and then your name will have the top directory. So how do we make this into Rust? First, some limitations. We say all items in a group must have the same item type, because that allows some nice static type checks for the hierarchy. I think most drivers do this anyway. So like when you create a directory if you go mkdir, it will always create the same layout of the subdirectory. Although I believe some drivers, they switch on the name and say like, if it starts with this, then it's this kind of thing you're configuring. Or if it matches this pattern, then it's something else. But for now, I just said, okay, let's keep that just like one kind. And then the item types, we require they have static lifetime, and that if you look at the C drivers that exist, they usually also define all the properties with macros provided by Configfs statically, so they know ahead of time. No one is like going, oh, if let's dynamically build a list of files to appear in this directory. And no binary attributes. And also, because items and groups, it doesn't make sense to have, groups can have sub-folders, and items cannot. But it turns out if you do not populate the vtable pointer that is responding to create directory, then you just get similar to as if you had just had an item. So you don't need to be able to create items. You can just create groups, and then if you don't want subfolders, you just don't populate that pointer, and then it's the same. So let's not have that. Okay, so first we define the subsystem structure for Rust. Now this is a namespace inside Configfs something, kernel Configfs, so it will be not like a random subsystem, but Configfs subsystem. And inside that we have our C thing here, Configfs subsystem. And then because the callbacks you get in Configfs on the C side, they don't pass along a context. So you don't usually, in a lot of places in the kernel, you will see there's like some void pointer and you can store your private data at the end of your entry. You don't have that in Configfs. The only thing to identify what you're operating on is the function pointer that you install in the table, so the address of that, and then the name of the attribute you're working on. That's how you ID stuff. I think that I like having if I'm exposing a data structure through Configfs, I think it's nice to have that data. Just get a pointer to that. So I added that in. That's what I put in here. We make this struct generic over this thing. So I can put in whatever, and at compile time, it's monomorphized to fit that particular type that we put in. And we put this C structure into an opaque, which is a marker type. In Rust, usually, if you have, not usually, in Rust, if you have a mutable reference to something, the compiler will emit no alias annotations for the LLVM IR. And that makes the compiler assume that if you have a mutable reference to something, no one else is going to mess with that. But if you pass it into C, and the kernel will do stuff with it, then obviously you have to, if you want to read a field of that, you have to reread it after. Otherwise, you're not going to see the changes your C function did. So that's just what that is. Opaque. It does a little bit more, but that's the main point. And this is big enough, right? So to initialize it, we put a name, string, and we put an item type that is also generic over this data field that we have up here. And we put a constructor for our data field. In Rust, we have move semantics by default. And a lot of types in the kernel, you can't just move them because then they become invalid. For instance, a mutex, depending on how you configure your kernel, it will have a linked list inside it. A linked list should be initialized to both pointers pointing to itself. And if you move this structure to somewhere else, these pointers are going to be pointing to the old place. So obviously we can't do that. Also, when you just allocate a linked list, it's actually not valid in C, and that might be, of course, you might say, but in Rust, when you allocate a data structure, it has to be valid because of the memory safety guarantees we have. So therefore, we have this pin init type here, which is an initializer that will give you back a reference to the thing that you're building only after it has become valid. So we sort of hide the step of the invalid data from the user and make it impossible to ever obtain a a linked list where the pointers have not been set to point to itself. I hope that makes sense. Otherwise, please ask. We can go into more detail.
What does pinning do?
So if you have a linked list in C, you allocate the OR mutex which embeds a linked list. When you just allocate that, probably the next and previous fields are set to 0. And this is why you have to call mutex init before you use it. Otherwise, those are pointing, the state of the structure is not valid. That's illegal in Rust. Whenever you have a reference to a piece of data, it has to have assumed a legal value. That's part of the memory safety guarantees. So pin init is something that implements a function that will, given a place, so a pointer to some a pointer to a place where you want to initialize the thing, it will initialize it and return a reference to the place for you, with all the initialization done. And that way we can work with the C types in Rust that has this requirement.
Okay, so it's the C type, but isn't this just a constructor?
It's a constructor, exactly.
It's the C type that you need this special type to work with the C.
We needed to be able to work with the types in C that require initialization to not segfault when you look at them. Right? So if you take the mutex and you just forget to init it, it will you will get a core dump or something because you deref the null pointer.
So the actual constructor will call the C constructor, which does not init.
Yeah, either call the C constructor or set up the structure in some other way, in such a way that it has a valid bit pattern. In native Rust, like when you allocate something, it will always have a valid bit pattern. But when we allocate space for a mutex or a linked list struct, that doesn't happen automatically. So we have to ensure that. We use the pin init for that. You saw over here, this one is annotated with pin data, and this field is annotated with pin, meaning that when we allocate this and provide this pin init constructor, it will sort of magically be taken care of for us.
Okay, so the whole pin thing is like a Rust for Linux specific thing?
It's built by people in Rust for Linux, but I would say it's not a Rust for Linux thing. It's a combining Rust with languages, other languages, right? So it's applicable everywhere you interface other languages. And it has also become a library for user space Rust that you can use, and it's used for various purposes. Right, so similar, so we have this, it's like the pin thing is a whole other like chapter about how we ensure that we don't move stuff that shouldn't be moved. But, so drop is a destructor. Now we have our subsystem, we implement a drop for that. That means when this goes out of scope, or when it's the last references to it is dropped, or when it's like when its lifetime ends, we call the drop function, similar to a destructor in other languages. And here we have a pinned reference to self, which is again pinned just means you can't move it. And to destroy this, we unregister the subsystem and we destroy our mutex. So just a destructor. But now we have the beginnings of this. Now if we want to implement a kernel module or a driver that uses this, it would look something like this. For Rust drivers or kernel modules, we have we define a struct and then we implement a trait on that struct, and then it can be used as a kernel module, and it will become like a loadable kernel module. A trait is like an interface. You say to implement this trait, you implement these functions, and now you're a kernel module. One of them is init, which corresponds to the like the C kernel init module init function. We get a pointer to the module. And so what we do is like we say hello, and then we try to initialize the type self, which is the type that we implemented on. And we construct a subsystem here. We say we want to be, our name should be Rust Configfs. So this is from the samples folder. And we want this item type, and we want to put the data field should be a struct called configuration that I didn't show, but imagine in there we could store whatever it is we want to expose through this file system, pseudo file system. And we will get a reference to this struct when the callbacks happen from the kernel. Now we just need this guy, right? Describing the contents of a directory. Should go up here somewhere, like item type equals, and then we can put it in here. So the C structure is config item type. We do the same thing again, just create a struct, and we put this item type inside. Now this item type, remember I said a subsystem is a group, is an item. So this item type can be for a subsystem or a group. Same, because they are the same, right? And I make it generic over this container that they're in. And we still have the data which corresponds to the thing we want to pass along with our callbacks from the kernel. Now we want to construct this item type. Let's see. We have this is just to construct something in Rust. You just do the name of the type, brackets, and fill out all the fields, similar to a struct constructor in C. Similar but different. And we have the field item type, where we construct this opaque, and inside that, the opaque was the one that made sure we had removed the no alias when we mutable access this. And then we put the constructor for the C struct inside, and here we have all the fields that the C struct takes. It has an owner, it has some group operations, which in this case we do not implement because this constructor does not allow you to create subdirectories. If you wanted to create subdirectories, we would populate this. We have some item operations, and we have this attribute list, which is going to be a list of the files we want to expose. And yeah, that's it. No binary attributes. So the attribute list is this array, a null-terminated array, right? And because we define all of our attributes statically, we can make this generic over a constant that's known on compile time. So let's say we want to have 4 files. We at compile time know that how long this array will be. So it will, if we want to have 4 files, it would be have a length of 6, right? Because the last one is the terminator. No one asked what is the phantom data?
You have that in the previous slide.
Yeah, but no one asked, so I'm not going to explain.
No, it said later on with the container.
What?
It said below that it contained the container of the folder.
Yeah, well, yeah, it's a marker for if you put a generic and you don't use it, compiler will complain. I don't know why it is like this. It is like this. Just like say used, pragma used, right? Okay. Exactly. Okay, so we have this attribute list. It has a list of attributes that we define here, which are also just a wrapper of the Configfs attribute. Mm-hmm. It's we use it to type check. It's not used in the definition of the struct, but later when we add attributes to an attribute list, we can type check that the functions, the vtable that will take references to data, actually, that you don't supply a function that will take a reference to something else, so you'll have type confusion. We can type check that you aligned everything correctly, right? So,
but shouldn't it know that then? And then not need transfer data? Shouldn't it know that connection?
yeah, that would be nice. But it doesn't. So we add that, right? So if you were writing safe Rust, like only Rust, you'll be all fine. But because we are wrapping an existing C API, I'm sort of expressing the requirements of the API in Rust. And I'm making this type check. So I'm making it fail type checking if the types of the pointers don't align. And that means I don't need this particular generic in this definition of this struct, but I will have code elsewhere that checks. Okay, we have the attribute, which is the file that will appear. That one will have the show and the store functions defined on it. We define a generic here that is a trait we invent that's called attribute operations. That's what the user will implement and create a load, like a store and I think it's save and, I forget, load and store, save and or something. Display, render, I don't know. Show and store. And so here we have this trait, I hope it's readable, that the user will implement. So again, a trait is like an interface from other programming languages. You implement it, you say you have a type, and then you say, now I want to implement this trait, and you'll say, impl trait attribute operations, and you implement these functions, and now you satisfy the trait. So these are, store and show, right? And so here we see you, in this case, you have to implement store, otherwise you'll get a build error, but you can omit show, I think. And now we have to wire it up. So we have the trait that the user is going to implement, and we have the attribute list where we need to. So we have the attribute where we need to populate the vtable, the function pointers. But obviously those are C functions, right? And the ones we define in our trait are Rust functions. So we need to bridge that gap, and we do that by implementing on the attribute that's generic over the thing that the user implements a function that's callable from C. Put this extern C, and this function now gets C API linkage. And this signature matches whatever you have in the C header for Configfs. So you get past the, when the kernel wants to render your file to a stream, you get past the config item and the name of the file. And again, that's where I would like to have also pass context along, this whatever void pointer to my data somewhere. If you look at how drivers implement this, they usually index into like a global tree or something to find whatever object you're operating on. So what we do here is like we get the item, since we decided that we always use groups. We have no items on their own. We know that this item is embedded within a group. So we just pointer jump back and find the group, and we know the group has a data field at another offset. So we get that. And then we call this show function, which is what the user implements. And we pass the data, and we pass a place to write the output, which is this one, comes from the kernel. Please render your attribute into this buffer. And because we have, by API contract from the C side, we know that we always have a page worth of data to write to, and please don't write anymore, because then you have a buffer overflow. In Rust, we are so fortunate that we can have what's called a slice, which is a pointer to a place that includes length, And if you access out of bounds, you're going to get it's bounce checked at runtime if the compiler can't determine if you're in bounds. So you're going to get a crash, probably kernel panic, if you write outside of bounds. And then there's some error the error handling down here. So how will we use this? Like the TV chefs, I cheated at home and made a macro that wire all this up together. And the way we can use it is now we call this macro Configfs attributes, and we put our subsystem in this case, and we have the configuration struct that stores our data. We have to repeat that here for reasons. And then we have one attribute, which we call my attribute, and we give it index 0. Now, you might have seen here, there's an ID here. That's to differentiate the implementation of this trait for different files. So you implement the trait many times, once for each file. Now we just have one, so we put 0. And so we implement the attribute operations for number 0, which is my attribute, and we render, write something. In this case, we just construct yeah.
Why don't you make a string? Why does it have to be a 0?
Because I don't think I can be generic, constant time generic over strings, and I wanted this to be constant. You see, I have a const ID here, and I think Rust does not support this being a string. So, and this is why, because it would be more great if it was, yeah.
I mean, when I read the code and I'm going to look for a file, then I need to know the index of that file.
Yeah, I agree. That would be nice. It's sort of confusing that it's just a number. You can if you are you could write dead beef or something, and then you can maybe
Yeah, but you can also bit shift it.
bit shift it.
Yeah, so you 8 bytes, just shift them in, so you have the bytes stored within the easy spot.
Sure. Yeah, sure. Anyways, I think the language does not support that, but that would be great. I don't see. Probably there's a reason why. I'm not a compiler person. Yeah. Anyways, so we implement this vtable. There's lots of magic going on here as well, but you essentially just write vtable and you put the trait name, you put 0 because that's what you had the other place. And we create a byte string and we write that. And you see this can't ever go out of bounds because we have a slice. We have to return the length. So we do that. Nothing bad will happen, probably, if you return more, because the caller will 0 that for you, so you don't get. Okay, so now because it's a terminal, I had to try something, which is now we can run stuff. And so this is, I want to show the expansion of this macro. Maybe. So now, okay, this that's also unfortunate. But you see here, I have one attribute called bas. So it's not the exact same code you were looking at before. In this case, we have more layers. So we have a child and we have some grandchildren and stuff. This level of the hierarchy has one attribute called bas. And if we expand that, we get this code. Page up. So you see it statically defines this attribute where it does a bunch of unsafe stuff behind the scenes, which is written in such a way that it will always be safe. We have the safety comments elsewhere to uphold this, and you don't have to write this as a user, but the code that you write will expand into this. You see, we have the attribute, and did someone say something? No. We have the size of this array that this null terminated array is calculated by the macro. This is sort of recursive expanding macro. So you will see like 1 plus 1 plus 1 plus 1 plus, right? And then we have this add method on the attribute list that will to insert this attribute into the list, and that will do a compile time check that you're not overriding the null terminator. So if you wrote this yourself and you actually overwrote the null terminator, you would get a compile time error. And then we construct this item type for this group and return that. See if I can figure out how to close this. Okay, so let's try it. Maybe. Maybe. So we're and samples. So let's go to the Configfs place, which is this kernel config. See, we have our module here. And we have 2 attributes here. Let's, so it says hello world, you didn't see, but that's what I put in the code. You can see there's nothing in there. Right, so it comes back. We can create a directory. You get the point, right? I think if we do that's the end of the line. The last hierarchy level didn't populate the make group pointer. Code is up. Actually, it was just merged yesterday, so it's now in mainline, and like it will be in 6.16, I guess. Well, that's it. Yeah, I hope it was useful and interesting in some way. If not, please let me know later in the bar.
Anybody? Questions?
Otherwise, I'm around. So.
No coffee?
Thank you. About sysfs and Configfs, I just read a code a bit, and I realized that not many people know actually that sysfs allows to write 4K exactly and requires 2 pages for that. And Configfs only allows to write 4K minus 1. And that's why it's different between sysfs and Configfs. And also, but my question mainly about that you mentioned that Configfs and sysfs similar in that sense, that also they are ABI. And people should know that if they do something with Configfs, it cannot be undone. So be careful with that.
What do you mean it cannot be undone?
I mean, if you put some code in the kernel upstream with Configfs, then you cannot change it, like names of attributes and everything.
Oh yeah, because it's user
It's
space.
ABI.
Yeah, sure. But the -1 thing is interesting, I think.
Yeah, basically many people doesn't know that sysfs actually requires 2 pages for attribute if you write 4K exactly.
Yeah,
for null terminator.
I'm gonna go have to go back and check like what I do if I get that bound correct. Seems important.
More questions?
What's the name of the tool you used for the slides?
It's a present term. Presentrm. Present term. Yeah, so you input Markdown, and then it comes out this. Right?
More? Last chance? Okay.
Thanks.